Hello viewers, welcome to my channel Chem Corona. In this video, we are going to discuss morphine, its chemistry, mechanism of action and SAR. So, morphine is basically used as opioid analgesics. What are analgesics? Analgesics are the agents that are used to relieve pain, whereas opioid analgesics are also called as narcotic analgesics or mu receptor agonist. These drugs, they act centrally, they relieve the pain and they have the ability to produce dependence. Opioid analgesics, they bind to opioid receptors which are situated in the spinal cord, and hence the name is opioid analgesics. They induce sleep in presence of pain, and they also suppress cough and facilitate anesthesia. At the same time, these drugs have some limitations such as depression, pruritus, decreased GI motility, and increased biliary tract pressure. So opium analgesics, they are obtained from opium poppy, that is Papaver somniferum. It is also called as sleep bringing poppy. There are many varieties of this opium and they are available in different colors. It is obtained from poppy seed and latex from the pod. It can be used as a tincture or it can be smoked. Mechanism of action of morphine. Opioid receptors are G protein coupled receptors. Opioid analgesic drugs, they bind to opioid receptor and induce analgesic action. So there are different types of opioid receptors, that is mu receptor, kappa receptor, delta receptor and sigma receptor. Mu receptors, they produce supraspinal analgesia, especially mu1, and spinal analgesia is induced by mu2. They also produce euphoria and physical dependence as well as meiosis. Kappa receptors, they produce supraspinal analgesia, that is K1 or kappa 1 receptor, and spinal analgesia by kappa 2 receptors. They also produce respiratory depression, dysphoria, hallucination, sedation and meiosis. Delta receptors, they induce spinal analgesia, respiratory depression and affective behavior. Whereas sigma receptors, they are least considered because they are neither activated by morphine nor blocked by naloxone. So this is the timeline of development of morphine. It was isolated in 1803, then in 1833 it was purified, in 1853 it was used as a medicine, and then in 1968 its structure was confirmed. You can see this is the structure of morphine. Now let us discuss the general structure of morphine. It consists of A ring, which is aromatic ring, then B ring, which is cyclohexane ring, C ring, which is cyclohexene ring, and D ring, which is piperidine ring, and ring E, that is tetrahydrofuran ring. So you can see here, this is A ring, which is aromatic, this is B ring, which is cyclohexane ring, this is ring C, which is cyclohexene, this is ring D, which is a piperidine ring, and this one is ring E, which is a tetrahydrofuran ring. Let us discuss the numbering of morphine. The numbering starts from ring A and it ends on ring E, D, which is the nitrogen containing ring. So the numbering starts from here, that is ring A. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 and 17. That is, it ends on the nitrogen of ring D. So ring A, it contains phenolic hydroxyl group at third position and alcoholic hydroxyl group at sixth position. There is a presence of a double bond at position 7 and 8, that is alicylic unsaturated linkage. And nitrogen atom is present at position 17, which is a tertiary nitrogen. And ring E contains ether bridge. So ring A has a phenolic hydroxyl group. Ring E has an ether bridge. Ring C, it contains alcoholic hydroxyl group at position 6 and there is a presence of alicylic unsaturated linkage at position 7 and 8. Ring D, it contains tertiary nitrogen. Now let us discuss the SAR of morphine. SAR of morphine can be discussed in 4 parts. That is, first is modification on phenyl ring, second is modification on alicylic ring, third is modification on tertiary nitrogen, and fourth is epoxide bridge. Let us discuss this one by one. First, that is, this morphine, it contains 5 chiral centers at position 5, 6, 9, 13 and 14. The configuration of these positions is 5R, 6S, 9R, 13S and 14R. Aromatic ring A and basic nitrogen, they are essential but not sufficient to produce analgesic activity. Aromatic ring A and nitrogen are connected by either ether linkage at 9 and 10 position or by propyl linkage, that is the edge of piperidine ring which forms ring B. Now let us discuss the SAR. The first point is modification on phenyl ring, that is ring A. So this aromatic phenyl ring is essential for activity. The free phenolic group gives optimum mu receptor affinity. It decreases with lipid water partition coefficient, but it leads to first pass glucuronidation, which results into poor bioavailability. So you can see here, this is the structure of morphine. It contains hydroxyl group at 3 and 6th position. Introduction of 3-methoxy group yields compound that is codeine. Codeine is a weak mu agonist. It undergoes metabolism by O-demethylation of codeine to morphine. Modification on phenolic hydroxyl group decreases the activity and etherification increases antitussive activity. Any other substitution on phenyl ring diminishes the activity. Second is modification on alicylic ring C. 6-hydroxyl can be converted to 6-methoxy, ethoxy or OCOCH3. It increases the analgesic activity. The natural conformation of C6 is alpha, but inversion to beta increases the mu receptor affinity. Removal of this 7-8 double bond, that is this 7-8 double bond, and conversion of alcoholic group to ketone increases the potency. Example is hydromorphone. You can see here in hydromorphone, this OH is converted to C double bond O and there is absence of the double bond which is present at 7 and 8. 14 alpha hydroxy and 6 keto derivative increases mu agonist property and decreases antitussive property. Example is oxycodone. You can see here, that is conversion of this H to OH, and conversion of this OH to C double bond O leads to oxycodone, which is having mu agonist property. Modification on tertiary nitrogen, that is tertiary amine is necessary for opioid activity. N-methyl substitution shows good agonistic property, increasing the number of carbons from 3 to 5 in substituent on nitrogen, or having double bond or small carboxylic ring results in antagonistic activity. Example is naloxone. But still, increasing the size of substituents such as N-phenylethyl substituent yields more potent mu agonist. And the last is epoxide bridge. Removal of the 3,4 epoxide bridge in morphine leads to morphinone series. Example is levorphanol and butorphanol. You can see here there is absence of the ether bridge. Morphinones can be prepared synthetically. The levoisomer has opioid activity, whereas the dextroisomer has antitussive activity. Levorphanol is more potent analgesic than morphine. So thank you for patient listening and happy learning. Like, share and subscribe my channel Chem Corona.